In this example, we're being asked to integrate 1 over x squared on the interval from 1 to infinity. Now, we're not going to be able to handle this like a traditional area under a curve problem because there's something about this integral that violates the fundamental theorem of calculus. The fundamental theorem of calculus really had two conditions for the integral. The function had to be continuous on the interval that we're integrating over. And second of all, the interval had to be finite. So that's what's actually being violated here. We're integrating from 1 up to infinity, which means the fundamental theorem of calculus is not going to be applicable here. So this type of integral is called an improper integral. And so hopefully we know how to handle this. I've made up some videos that you've hopefully already watched on how to handle improper integrals like this. But the idea is going to be simply this. We're not going to integrate from 1 all the way up to infinity quite yet. We're going to integrate from 1 up to what I'll call B or K, or you can pick a letter. The letter B isn't that important, but up to some kind of floating constant, if you will, of 1 over x squared dx, and graphically it's going to look like this. Okay, if here's 1 right here, we're going to integrate from 1 not all the way to infinity, but we're going to stop. We're going to stop at b. Right now, if we stop at a defined spot like b, then we can do the fundamental theorem of calculus because this is now a closed interval. But obviously this answer won't be our answer because we still have this missing area back here. So how do we account for that? Well, after we compute this definite integral here, notice it'll have b's in my answer because we'll find this indefinite integral or the antiderivative basically, and then we'll plug in b and plug in 1 and subtract. So our answer is going to have b's. So for the b's that are in your answer, we will then turn back around and take the limit as b pushes its way on the rest of the way to infinity. So it's really like using a backdoor type of technique to really get what you want, and while still being able to use the fundamental theorem of calculus. All right, so let's integrate this guy first. The integral of 1 over x squared, that would be negative 1 over x. I'm not going to go through those details. I think we can probably do that with a 1 to a b. And then we still have this limit out front. Limit is b goes to infinity. All right, then we'll plug in a b and get negative 1 over b. Negative 1 over b. And then minus, let's go back here, minus, let's plug in a 1 and we get negative 1. So negative makes a positive 1 in fact. There's our definite integral. Notice it still has a b in the answer as I was mentioning earlier. So now that that's finished, that would be the area up to some kind of like floating b value. So if we ever got around to telling it what b should actually be chosen to be, like 10 or 12 or 20 or 100, then you could quickly just substitute that b value in here and you'd have your answer. But I don't want b to be any finite value. I want to push my way all the way out to infinity so that it's equivalent to the original integral. So that's where the limit comes in. So now we're going to take the limit of this, right? The limit as b goes to infinity. That limit obviously exists, right? As b goes to infinity, 1 over infinity goes to 0, and 0 and 1 make 1. All right, good deal. So we got a numerical answer. What is that numerical answer? What does it mean exactly? Well, if we trace this back to the beginning of the problem, this is the area under the curve from 1 all the way out to infinity. Now, at first glance, you might not be inclined to believe that because you might, if your logic was like mine the first time I heard this when I was in calculus, I thought to myself, how can you integrate over such a long interval? It's infinitely long from 1 to infinity, yet get a finite amount of area. It's kind of difficult to wrap your mind around. Well, here's kind of a layman's explanation of what's going on here. this function 1 over x squared is not only going to 0, right? 1 over x squared does go to 0, but it's going to 0 extremely fast. And so if this function goes to 0 quick enough, it in some sense pinches off the function to where you would only get a finite amount of area, even though the interval is infinitely long. If this thing went to 0 but it went too slowly, then you could still accumulate lots and lots of area, and this integral could easily be infinity. But for us, it winds up being the number 1. Now, if I have time, I'm going to try to squeeze in one more quick example here, just so you have two to kind of contrast against each other. It looks almost identical, but this time it's only 1 over x, from 1 to infinity. So we're going to employ the same idea. We're only going to go from 1 up to b, and then we'll take a limit, and we'll let b go to infinity when we're done. So limit as b goes to infinity, integral from 1 to b of 1 over x dx. Integral of 1 over x is the natural log of x. Bracket from 1 to b with the limit out front. Limit as b goes to infinity. All right, now natural log of b, right, you have the limit as b goes to infinity. Natural log of the absolute value of b minus the natural log of 1, but the natural log of 1 is just 0. So that's kind of odd. So we won't have that term. And now as b goes to infinity, where does natural log of b go? Well, it also goes to infinity. So that's interesting. So this is not a finite numerical value for this answer. So what does all that mean exactly? Well, what we say is that this integral diverges, or the limit diverged, and so this will diverge, right? We don't actually have a numerical answer for this improper integral, where this one from before we did have an answer. Now, what was it on a more practical level that made this not have a finite amount of area on the interval from 1 to infinity? Well, it kind of goes back to what I was saying earlier. Here, 1 over x decays much more slowly versus 1 over x squared, which decays very, very quickly. And it's a little too slow, and it allows us to accumulate an infinite amount of area as we go from 1 to infinity, basically. So here we've seen two different types. One that where the limit existed, one where the limit didn't exist. And so hopefully that helps you understand this type of improper integral just a little bit better.